Hello, this is Mr. Molikash again with your Calculus 1 video of the week. Calculus is tough work, it's tough business, and I just want to give a shout out to my students that are hanging in there and still digging down in the trenches with Calculus 1. It's tough to learn online, especially. So what we're going to do is we're going to talk about a couple of things. So on the agenda for today, let's see if I can just type this out. So on the agenda, we're going to talk about some consequences for differentiation, some things that happen when a function is differentiable, and we'll talk about what that means if the derivative exists at a point. I'll briefly mention what a one-sided derivative is, because I meant to talk about that in an earlier video and didn't. We'll need to discover what the derivatives of trig functions are, and all 6 of them. And the big thing for today is something called the chain rule, which is how to differentiate a composite function. And a consequence of the chain rule is to be able to differentiate implicitly defined functions. So we'll call this implicit differentiation. So yeah, we have kind of a tall order to talk about. So one of the things about derivatives is that if a function has a derivative at x equals c, then it must be continuous. For my students in recent assignments, that you've been asked a lot of questions about continuity, to justify whether a function is continuous or not, using the 3 conditions in the formal definition. Many of you didn't do that. You kind of used some different verbiage. But remember, for a function to be continuous by definition, it has to have a function value, it has to have a limit, and those 2 have to equal each other, right? So those 3 conditions can kind of be cumbersome to show, and it's much easier in many cases to show that a function is continuous by just knowing that it has a derivative at that point. So you might be wondering, like, what does it even mean to have a derivative? So I'll talk about that too. But what you need to know about this is a theorem, and it says differentiability implies continuity. But the converse of this is not necessarily true, and therefore it's not true. Okay, so if a function is continuous at x equals c, you may or may not have a derivative at x equals c. And so I'm going to show you a couple of examples. Let me draw just a function that has a nice smooth curve to it, something like this, and here is a value of c, right? And so if I go across the way here on the other axis, we have f of c. Okay, and then I can draw the tangent line here, right? So the tangent line exists. I didn't do a terribly good job drawing that, but anyway, the slope of this line is f prime of c. So if we have a tangent line with a defined slope, not a vertical tangent line, because vertical lines have no slope, right? But horizontal or slanted in some way, If that derivative exists, then the function must also be continuous. Okay, that's what this function is. That's what this is saying. Okay, but if you let me rewind a little bit, and I'll try to hit the undo button on my pen software. By the way, if you're a Mac user, I don't work for Epic Pen, but this is Epic Pen, much better for Windows than Mac, but it's the best thing going, I think, for Mac, because you can draw over the entire screen. You don't have to just stick to drawing in a specific window. So anyhow, enough about that. Enough for a little infomercial on Epic Pen. But let's say that our function looks something like this. There's a function like that. Okay, and then we'll let that point be ordered pair C comma f of C. Okay, and it's in this case, we have a function that's continuous, but the derivative doesn't exist. So let me make a remark about this particular function of this graph. F prime of C does not exist on this graph, even though it's continuous. Okay, the limit of the function exists, so the limit as x approaches C from both sides of f of x is actually f of C, but the slope of the tangent line is a little bit ambiguous. I mean, on one side you have like maybe a slopes that are positive, right, are getting more positive, and on the other side you have slopes that are getting more negative, right? So on one side it's more positive, on the other side it's more negative, and well, the derivative doesn't exist in that case, right? In fact, one could argue that the slope of here would be, the tangent line might even be a vertical line, and the slope is nothing. There is no slope of a vertical line, right? So it's important to understand that the converse of this is not true. However, if you do have a derivative, the function must also be continuous. So that's really good news, and it's an easier way, to be honest with you, to show that a function is continuous in many cases. Okay, so I want to talk a little bit about a one-sided derivative. What is a one-sided derivative? Well, if you remember the definition of the limit definition, right? What is the derivative of a function at C, right? What it really is that? It's the limit as h, sorry, let me repeat that, limit as some quantity h approaches 0 of the function f evaluated at C subtracted from the function evaluated at C plus h. So we have a y2 minus a y1, right? And then if you take all the f's away, if you were to do C plus h minus C, you would just get h. Okay, and if you plug in 0 for h, you get 0 divided by 0, which is undefined. However, we've found out that due to some techniques that the limit does exist oftentimes. And a one-sided derivative just takes this, really, to be honest with you, it takes the either the c value from one side or the h value from one side. So maybe, instead of doing, negative h's that are less than c, we have to do h's that are greater than c, or that kind of thing. So, sometimes you can have a one-sided limit that looks like this, right? And what I mean by that, like, for example, let's say that, let me just throw an example at you. Let's say that we want our function to be the square root of x cubed. So what does that look like, right? Square root of x cubed. So what it actually looks like is, well, I can just quickly show you a Desmos graph, I guess. Let me do that real quick. So let me hide my ink here. Let's just go ahead and graph that real quick, and I'll show you the square root of x cubed. Okay, so you can see, like, for values that are, when x is less than 0, you'd be taking the square root of a negative number, right? So this function isn't even defined on the left side of 0, but one might argue like, well, how do you find the slope of the tangent line here? And you can, but it's a one-sided derivative. So your h's have to be on the right side of 0. You don't want the h's to be negative on the left side of 0. So it's just really important that you're looking at one side of the c value. Okay, so in this case, let me put that back again. If you asked, or if you were asked, okay, to find f prime of 0, okay, then you're really doing the one-sided derivative, because you're only taking the limit from values that are greater than 0 and not less than 0. All right. So you could do this, and this derivative actually exists on the right side of x equals 0, or as x approaches 0 from the right. Because remember from last week's video that we can rewrite this as x to the 3/2, right? And so you could just do the power rule and reduce that by 1, and then we'd evaluate this at x equals 0, right? So f prime of 0 is 3/2 times 0 to the 1/2, and we know that the 1/2 power is just a square root, and the square root of 0 is 0, and that's definitely a number, right? And 0 times anything is 0. So what happens at that graph is that you have a horizontal tangent line. So I'll go back and show you that, and then we'll move on to the derivatives of the trig functions. If this works out. Yeah, epic pen, it's really fun. Okay, so let me draw the x-axis, otherwise known as y equals 0. And so I want to show you what it means to be differentiable from a graphical point of view. So let's zoom in on this point 0, 0. You see that the curve kind of goes up and to the right away from the x-axis. But what we're going to do is we're going to zoom in. This is the reason I'm using Desmos right now as opposed to Maple, because I can animate this graph. And as I zoom in, you can see that the values on getting very, very close to 0, right? So I'm negative 1/10 and positive 1/10. But you see what's happening to the red graph as I'm zooming in? It looks like it's getting closer to the x-axis, doesn't it? And so if we say this as mathematicians a lot, if the graph is locally linear, which means that if I zoom in enough, if I keep zooming in enough, okay, you won't be able to tell. Let me remove the grid and the axes. If I zoom in enough, you won't be able to tell the difference between the line and the curve. So if we zoom in very, 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 very close to x equals 0, you can see that it looks like y equals 0, but only for values greater than 0, right? So you could say that it's y equals 0, but x greater than or equal to 0. So it would be like this, right? So that's the reason why we call it a one-sided derivative, because the derivative is not 0 on the left side. It's only 0 from values x equals 0 approaching 0 from the right. Okay, so I just wanted to show you that real quick graphically, and if we zoom back out again, way out, and keep zooming out, keep zooming out, keep zooming out, this is what happens. Like the curve has values that are going away from the tangent line, but as we approach 0, 0, the graph sure does look more and more like this blue line. Okay, so that's for the most part what a one-sided derivative is. All right, moving on, we're going to look at the derivatives of the trig functions, all 6 of them, and I happen to have that right here, so let me copy that and put that here. Whoops, forgot I'm using a Mac instead of a PC. But here they are. I just copied them straight out of your textbook. And what I'd like to do actually is to prove one of these. I don't have time to work out all 6 of them. But what I'd like to do is to kind of reinforce the quotient rule from last week. So we're going to let y equal tangent theta. So our input variable is not x, it's theta in this case. But remember, we can write this as the sine of theta over the cosine of theta. And so this is our f and this is our g, right? Let me kind of point that out. We're going to let this be f and this be g. And our y prime, remember the quotient rule, right? It is, for the quotient rule, it's low d high minus high d low over low squared. So what is my g? It's cosine theta times f prime. Okay, so f prime, I need the derivative of the sine. The derivative of the sine is cosine, so that's going to be cosine again. By the way, the proofs of this one and this one are in the book. You can look at the limit definition if you want to read. It uses the sum and difference formulas from Math 172 if you're one of my students, or from your trigonometry days. You learned about that in your pre-calculus. All right, minus. So the high is sine theta. And the low prime, the derivative of cosine, according to this, is negative sine theta. So we have a negative sine theta. And then all this is going to be divided by the square of the denominator, right? Cosine squared. And let's clean this up a little bit. So up here we can write that as cosine squared theta, because it's cosine times cosine. And in here, a negative times another negative is a positive. And well, we remember from our trigonometry days as well that, well, cosine squared theta plus sine squared theta is a Pythagorean identity that actually equals 1 for any value of theta, for all values of theta. Doesn't matter what you put in there, this is always going to equal 1. And then, of course, we remember, too, from our trigonometry days that the reciprocal of cosine is called secant. Okay, so that is the reason why the derivative of tangent is secant squared theta. There's a lot of trigonometry involved behind the scenes. And you can do some more tricks of the trade. For example, with cotangent, you can do cosine over sine and do the same kind of business. For secant, you can do 1 over cosine and do the same kind of business. For cosecant, you can do 1 over sine and do the same kind of business. But again, I would kind of refer to your textbooks. I'm not going to include that in today's video, like why these are what they are. So read up in your book and see, you know, for example, one of the things that they do is like if you had to do the sine of x plus h, right, minus the sine of x over h, right, you'd have to use the sum and difference formula. So it's sine cosine plus cosine sine. They do this kind of thing in the book, and then you have, you know, you've got to do some more simplification, right, to, you know, factor and group things and all that kind of stuff. But eventually, if you take the limit of this as h approaches 0, you wind up getting just the cosine of x, which is kind of cool. But for now, you know, you're just going to have to believe me that those are what they are, and we can, you know, develop, I guess, the derivatives in 3, 4, 5, and 6 from the quotient rule. Okay, so those are the derivatives of the trig functions, all 6 of them. You need to know them, you need to have them memorized so you can quickly recognize them and be able to write them down from memory. Okay, alright, so the big enchilada, one of the biggest part of this video, to be honest, is the chain, what we call the chain rule. The chain rule is probably the most important derivative rule you will ever learn. If you go on and take Calculus 2 and Calculus 3 and then go on and take differential equations, if you do any work in graduate school with calculus and the theory of calculus, calculus of variations, anything having to do with calculus, the chain rule is really up there. It's super, super important. And what the chain rule does, is it allows you to find the derivative of a composite function. So let me paste that here. That's what the book says the chain rule is. And I kind of want to present this a couple of different ways, okay? Because composite functions give people all kinds of fits in, you know, their earlier math classes. So what a composite function is, you know, let's say that you have two functions. You have y equals f of x, and you have another y equals g of x, right? But then if you want a third function that's composed of two of these, you can compose them two ways. You could take f, and instead of letting the input variable being x, you put the entire function in. So that's what a composite function is, right? It's instead of f composed of x, it's f composed of g of x. And so you might have to go back and revisit all your, you know, how to find f of g of 3 or f of g of x algebraically from your previous classes. But if you have this kind of thing, right, the derivative of f of x, you know, we're just going to call f prime of x. And, you know, sometimes we'll use dy dx. In a little bit when we do implicit differentiation, we'll use dy dx instead of y prime. So remember, the Leibniz notation and the Lagrange notation are both equivalent. And so the derivative of y here, whoops, let me go back and fix that little mark there. The derivative here would be g prime of x, right? But it turns out that the derivative of this thing is a little bit more. It's f prime of g of x, but it's got a little bit extra tacked on to the end. And I want to explain why that has to be there. And it has to be there. There's something else on the end of that, and if you forget it, I have a specific set of skills. I will find you, and I will teach you the chain rule. I will not kill you. I am not Liam Neeson. But anyway, what needs to go here is the derivative of the input function. So it's kind of like the outer function f is chained to the inside. So it's the derivative of the outer function with the original input times the derivative of the input. That's kind of what they're saying over here, right? F composed of g's derivative evaluated at a number a, and I used x instead of a. So we could have just replaced all those x's with a's or b's or c's or whatever. But you take the derivative of the input, the output function with the original input, and then you tack on or chain on the derivative of the input function. And to be honest, like even up here, we're still doing the chain rule. There is a 1 attached to these, right? And you might be saying, well, why did you put times 1 there? Well, the reason is because the derivative of x is 1, right? The derivative of x is 1. We never bothered to write times 1 because it's kind of pointless, right? Multiplying by 1 doesn't really do anything, but all the while, really, we were doing the chain rule all along with all our derivatives. So I say all that to say this. If the inside of your function is more complicated than x, if it's x squared, if it's sine of x, if it's something else besides x, you got to tack on its derivative. Okay, so we're going to do a couple of examples because, like I said, this is like the big kahuna rule here, right? So what I'd like to do is I want to do the derivative of this function, and I'm going to do it in two different ways. Partly because I want to review some things from last week's video. So one way we could do this, okay, using the power rule from last week, is to multiply all this out, right? So let's go do some algebra. You heard me talk about that in a previous video. Let's go do some algebra, multiply all this junk by itself, so first, outer, inner, last. So then we have plus x cubed, which is plus 2x cubed, and then 1 times 1 is 1. All right, then finally we can do Now that we've done all our algebra, now we can do calculus with the power rule. So this is 6 times x to the 5th plus, all right, 3 gets to be moved down times 2, that's 6x squared, and then the derivative of 1 is 0, right? And that's a correct derivative, okay? Now, if we did this with the, so this is the power rule, okay? So if we did this with the chain rule, this is the way that the derivative would work with the chain rule, okay? We would say, hey, there's something squared. How do I take the derivative of something squared? I just go straight for the calculus. No algebra required. I'm going to use the power rule on this entire function. So I'm going to do 2 times all that mess to the 1, but, big but, and I cannot lie, I need to tack on the derivative of this inner function. I'm not done yet. I need to find the derivative of the inside. I need to look at my g of a and find its derivative, right? So what's going to be tacked on here is going to be 3x squared plus 0. I don't need to write the plus 0. I did over here, but I don't have to, right? And you might be wondering, like, whoa, is that the same thing as this? And first off, like, dude, you just did that in one step rather than having to do all this crap load of algebra. Exactly. So, and it is the same thing, right? Because if I do 2 times 3x squared, I get 6x squared, and then x cubed plus 1 raised to the 1 power. Whereas over here, I could easily factor this, right? I could get the GCF out, and I get x cubed plus 1. Of course, I never had to write the plus 0 to begin with, right? So it is the same thing, but man, was that easier or what? Yeah, it was. It's easy if you know how to do it, right? So again, let's kind of review what I did there. I used the power rule on this big function, 2 times that stuff to the 1, and then I tacked on the derivative of the stuff, the derivative of the inside, okay? So that's the way that you do the chain rule, and you implement this every time the inside is not x. That's what you do. So rewind the video if you need to see that again, but we're going to do a couple more examples. And in some cases, you're really going to want to do the chain rule. So for example, let's say that instead of x cubed plus 1 squared, I had x cubed plus 1 to the 5th. OMG, I do not want to multiply out 5 of those things, right? That would be a nightmare. I'd probably screw up the algebra before I ever got to the calculus. So what I'm going to do is just go straight for the derivative. I'm going to use the chain rule by moving the 5 in front. So I'm using the power rule on this big input function, and then I need to take the derivative of the inner function. The end, right? Now, if you're in a multiple choice setting, or if you need to simplify this for something, later on you're going to want to simplify your derivatives because we have to use them for things. So, you might want to clean this up and say 15x squared times x cubed plus 1 raised to the 4th power. But I wouldn't do anything else with it. I would not multiply that junk out. Okay? But yeah, it's that simple. So 5 times the stuff to the 4th, using the big power rule on the big function. And then I need the derivative of the function itself. Plus 0 technically, because the derivative of 1 is 0, right? We talked about that in the previous video. All right, let's do one more that has to do with our trig functions. So let's say that we have, earlier I mentioned that if y is the sine of x, whoa, what happened? What on earth? If y is the sine of x, then that automatically means that the derivative is the cosine of x. Okay? Alright, so what happens if y is the sine of some other thing, like the sine of x squared? See if you could pause the video and find out what the derivative is. Okay, so you're back, and hopefully you found the right derivative, so I'm going to tell you the big reveal. That is the cosine of x squared times 2x, aka 2x times the cosine of x squared. My students, if you write this down on a piece of paper, I ain't going to mark it wrong. Just know that this is the bottom is the textbook answer, and again, in the future we're going to need to simplify things because we're going to have to use our derivatives for stuff. All right, so super important. Now, what happens if we had to do the second derivative? Remember we talked about multiple derivatives last time? Well, in the second derivative, we're going to have to use the product rule, right? We have the product of two different kinds of functions. So this would be our f, this is our g, and remember the product rule says it's f prime times g plus f times g prime. Okay, so how would this work out, right, for this particular example? So our y double prime, okay, our f prime, the derivative of this stuff is just 2, right? Yep, okay, 2x to the 1, that's 2 times x to the 0, right? And x to the 0 is just 1. All right, our g is the cosine of x squared. All right, plus f, which was 2x. And then I got to do the derivative of the cosine of x squared. Whoa, what's that? Well, I need to use the chain rule for my g prime, right? So let me do a little bit of work over here, just a little bit of work. Like let's say if g of x is the cosine of x squared, then g prime of x would be the minus of the sine of x squared times 2x. Sorry, I kind of got off the whiteboard there, but it's negative sine of the inside times the derivative of the inside, right? So that's what's going to go here. That's our g prime. Negative sine of x squared times 2x, okay? And then, you know, cleaning all this up, this is, you can see this is looking pretty messy, isn't it? So this would be 2 times the cosine of x squared. Let's see, minus, plus times minus is minus, 2x times 2x is 4x squared, so this would be minus 4x squared times the sine of x squared. And that would be the second derivative of this function, right? So here's your function. Here is your derivative, which is right here. And then here's your second derivative. And yes, if you needed to, you could go on and do a third derivative. That would be complicated, but you'd have to do the chain rule and the product rule, and you can see, like, it gets complicated, okay? I'm not going to do any more derivatives for this function, don't worry. But okay, last thing I want to cover though today is the implicit differentiation. So let's talk about what implicit differentiation is, and then we'll be done with this week's video. So what is what does that mean? Like, what the heck is implicit differentiation? Back in the day, there used to be like these things you could buy in the stores. They were called CDs, and instead of like streaming music, you would put the CD in your little CD player, and you would hear the music that way. And you'd have to skip to the song that you like and all that. So when you go buy CDs or records in the record store, the music store, back in the day, they used to have parental advisory stickers on the albums, and it would say parental advisory, explicit lyrics, right? So explicit means it's all spelled out, like the F word is there, all those words are there. Implicit means that things are implied, right? Like I'm implying something, but I'm not spelling it out. So an implicit function is kind of like this. It's kind of like, well, here's an example of one. It's the unit circle, right? Now, I could rewrite that as two functions of x, right? I don't want to do that. I could solve this for x, and I'll just quickly tell you that this turns into two different functions. The top half of the unit circle would be the square root of 1 minus x squared, and then the bottom half of that would be the minus, plus or minus square root, right? So there'd be two different functions for that. And then, yeah, I could find the derivative of each one of these, and do one-sided derivatives, right? So like, all that kind of stuff. Well, it's a little bit cumbersome to work like that. So with things that are written like this, you can graph implicitly defined curves. In fact, you can do 2D plot of this in Maple, okay. And for those of you that are watching this that aren't my students, you can use your Desmos calculator, and you can certainly type x squared plus y squared equals 1, and there's your unit circle, right? Beautiful unit circle that we come to know and love from our trigonometry days, right? Wonderful. Okay. So let's say that I pick a point on this line and I want to find the slope of the tangent line to that circle, right? And the thing to do here is actually to use the chain rule. So here's what I'm going to do, okay? I'm going to explain how this process, this method of implicit differentiation works. And this is from the NC State textbook for my students. This is where I got this problem from. So to find dy dx, okay, what I'm going to do is I'm going to take this equation and write it down. I'm going to space out something in front of the 1. And I'm going to do something to both sides. I'm going to, listen carefully as I say this, I'm going to differentiate this expression with respect to x. I want to find the derivative of this with respect to x. And if I do that to the left side, I have to do that to the right side as well. And so finding the derivative, differentiation, is an operation that you can do to both sides of an equation. And the equation will stay balanced. It will still be equal on both sides. So I'm going to spell this out in kind of great detail for you. So I want to find the derivative of the x squared with respect to x. I also want to find the derivative of the y squared with respect to x. And straight away, I know the derivative of 1 is 0, right? The derivative of 1 is 0. The derivative of any constant is 0. So what's the derivative of x squared with respect to x? Well, that would be 2x times 1. And I'm going to pencil in that 1 for a moment. And the 1 is the derivative of the x. So really, I used the chain rule, right? I did 2 times x to the 1 power and then times the derivative of the x. And I'm being super technical right now. Normally I just write down 2x, but I'm explaining this for a reason. Okay, over here I'd have to do the same thing, right? I'd have to do 2 times y to the 1 times, now y, its derivative is not 1. In fact, the derivative of y is this thing. This is the derivative of y with respect to x. So I'm going to actually write that down instead of 1. Okay? So really what the 1 is dx dx. It's the derivative of x with respect to x, and everything cancels out and you get 1, right? But we never have to write that down, but technically, like, that's what's going on under the hood there, okay? So you never need to write dx dx, it's kind of pointless. And you don't have to multiply by 1. I mean, the derivative of x squared is just straight up 2x, okay? However, the derivative of y squared with respect to x is 2y to the 1 times dy dx. And the reason I have to put the dy dx, here's another explanation for this. That variable does not agree with that variable. So dy and dx don't cancel each other out like dx and dx do. All right, so from here I get to do a little bit of algebra. I'm going to rewrite that, clean that up a little bit. So instead of 2 times parentheses y raised to the 1, I'm just going to do 2y. All right, so I'm going to get the dy dx. I want to solve this equation. Let me write that over here. I want to solve this equation for dy dx. And that's how I'm going to compute it. So I'm going to subtract 2x from both sides. And then I'm going to divide both sides by 2y. And so I have my expression dy dx equals, and of course the 2's cancel, So it's negative x over y. And the bizarre thing about implicitly defined derivatives is that you can have both x's and y's in the answer. In fact, the original black equation up here had both an x and a y on the same side of the equation. So I didn't get y by itself, I didn't isolate y, I didn't write y as a function of x to be more technical about it. I just left the equation written implicitly rather than explicitly defining what y is as a function of x. Okay, so this is what you would do. And then, like, if you wanted to find the slope at, say, let's say that you have your unit circle and you remember some of the points on the unit circle, like 1/2 and square root 3 over 2. So if I wanted to find the slope of this line, I put that number in for x and that number in for y, right? So let's see, the slope would be negative x over y, and that is negative 1/2 times the reciprocal of the denominator, right? And it's just negative 1 over square root 3, right? And by the way, it's fine to leave a square root in the bottom of a fraction. I don't care. WebAssign might care, so you might have to, what's that called? Rationalize the denominator, but I don't care. All right. All right, so last thing I want to show you is sort of why that negative x over y happens, okay? And I think this is kind of cool. This is a geometry thing. So let me just show you real quick before I leave you. I'm going to do the best I can to draw the unit circle here. Okay, so there's our x-axis and our y-axis, and let's just say that this point has coordinates x and y. Okay, and if you remember learning about the unit circle, you know that inside the first quadrant here there's a right triangle. Remember this? And the x coordinate of this point is, we'll call that 1. The x divided by the 1 is the cosine of this angle, right? And the opposite over the hypotenuse is the sine of the angle. So this is, x is always the cosine of that angle, and y is always the sine of that angle. So I don't really care too much about angles at the moment, but I just kind of wanted to review that with you. And what I really wanted to show you was this. Let me just get rid of that angle in there. Okay. If I wanted to find the slope of this line, what is the slope of the radius? The rise is y, right? I have to go up y units and I have to go to the right x units. So that is my rise and run, right? And you might remember from maybe your high school days or from geometry class that the slope of the tangent line is always perpendicular to the radius at the point of tangency. So a radius and a tangent always make a right angle with each other at this point on the circle, right? Okay, so the slope of the tangent line is the opposite reciprocal of the slope of the radius. And that is exactly what we got when we found the derivative earlier, right? So there's a little geometry that kind of proves that what we just did was right. It's that opposite reciprocal when you do the slope of the perpendicular line. So pretty cool stuff. But folks, I know calculus is tough. This was a lot of material. I cannot stress to you how important it is to make sure that you understand the chain rule. If you don't learn any other rule for derivatives, the chain rule has got to be it. Your life will be miserable as a calculus student in the future if you don't learn the chain rule. So get in the book, do as many problems and as many examples as you possibly can. Watch this video. Go to places like Patrick JMT or Khan Academy and just get as much practice as you can with the chain rule. But until next week,